Again, this is the high voltage cable, but now I would like to calculate the electric stress distribution in the insulation. Let's assume that the cable dimensions are unlimited. You cannot change the outer cable diameter, but you can change the cable inner conductor diameter. You can make it small or you can make it large. What would be the optimal dimensions of the inner conductor? If I make it very small, there will be the high electric field stress on the conductor surface because its radius is very small. And if you take a look, the cable, the electric field strength is distributed like this. If you make this radius very small, you will get the very high field stress. If you take the large, if you make the inner conductor large, very large, again you can get the high electric field stress in the insulation because the insulation thickness will be small. For large inner conductor, the insulation thickness is small. So there is some optimum value for this conductor diameter, which brings the minimal electric field strength on its surface. Can we solve this problem with QuickField? Of course, we can. I will start QuickField and open the problem. This is already created problem. You can take a look at the geometry model. This is the 1/4 of the full cable cross section. The problem type is electrostatics. I would like to calculate the electric field stress distribution. This is the insulation. The outer cable size is limited. You cannot change this, but you can change the inner conductor dimensions. The outer surface has grounded electric potential. And this is the aluminum shield here, which is grounded, and the central conductor has high electric potential. Now let me demonstrate the electric field distribution in this cable. Let's take a look at the result. I will switch on the color map of electric field strength. And by the way, this is the new feature of QuickField 6.3.1. You can set up the base lane of the equipotential lines. So I can set the lines interval to be 5 kilovolts and the baseline to be 0 volts. And namely these are 0 electric potential. These I will switch off the color map. 0 electric potential line, 5 kilovolts, 10, 15, 20, 25, 30, 35 kilovolts. Okay, let's back to field picture and I switch on the electric field strength. You see the electric field strength at this central conductor is about 12.4 kilovolts per millimeter. Now if in QuickField I made this insulation, this central conductor like this, this would be the conductor, this would be the insulation. And again switch on the color map of the electric field strength. You see the strength now is 18.1 kilovolts per millimeter. 12, 18. Let me try again. It is a bit bigger than initial, but smaller than our last case. It is 8.3 kilovolts per millimeter. So there is some optimum value near here that will bring you the minimum electric field strength. Now how should I find this optimum design? QuickField features the label mover tool, which is capable of optimization. How does it work? I will switch to the optimization and select the base problem. That electrostatic problem. I would like to optimize the design in this problem. Now, what values I could change? I can change the diameter of the high voltage conductor. For example, it could be 2 times smaller or 2 times larger. I will scale this central conductor, make it 2 times smaller or 2 times larger. This is the variation of the geometry. What values I would like to measure? I would like to minimize the electric field strength at this point. If you take a look at the geometry model, there is the point here, which is labeled by like point. There is no data in this label. It is used only for measurement. So I can refer to this point from the label mover tool. So for this point, no, not variation, add values. For this point, I would like to measure the electric field strength and make it minimal. So I have the base problem, this problem. I have the variation, the change in inner conductor diameter, and I have the value to optimize minimal electric field strength for this point. Now let's run the optimization. I will set to say 30 tries. Do optimization. You see, QuickField tries to move the high voltage conductor, to scale the high voltage conductor, simulates the problem, and calculates the electric field strength. The results are placed in the table. Well, my best result was 8.3, and with label more optimization the best result is 8.17. Let's take a look at this model. This is the sixth step. This is the model optimized, and let's take a look at the simulation results. I will build the contour and take a look at the electric field stress distribution. So at this point in the central conductor surface, the electric field strength now is better to see it in the table, 8.17 kilovolts per millimeter.